Welcome to this lecture on cryogenic hydrogen technology. You may remember that we were talking about the hydrogen production. So far we have talked about the hydrogen production from conventional route using the fossil fuel, and you may remember that we have talked about the different processes like steam reforming, partial oxidation, and then we have also talked about the autothermal processes and the different kind of fossil fuels those are in use, like starting from the coal, then natural gas, crude oil, naphtha, etc., and the different processes basically to produce the raw hydrogen, or say the syngas, and from the syngas we wanted to separate the raw hydrogen, and from raw hydrogen it is to be purified to get the pure hydrogen. So, that is what is the different those are the different routes of generating hydrogen. So, this syngas generation is the common industrial chemical engineering process which is widely used, and we have lot of experience. So, there is another way of generating this hydrogen. Now, we will be talking about that, and that is about the hydrogen production from coke oven gas. So, these are the today in this lecture we will be talking about a process called Linde-Braun process for separation of hydrogen from the coke oven gas. So, let us start. So, if we have to generate the hydrogen from coke oven gas, first of all we need to know what is coke oven gas, and before that what is coke. Coke is something like a porous macroporous element, and it is macroporous means its pore sizes are more than 500 angstrom. So, it is basically a carbonaceous material, mainly a particular grade of coal or its blend. Mostly it is made up from it comes from the bituminous coal, and with a particular grade of coal. Okay. And its utility is of course in the steel making, where this will be used for smelting of the iron core. It comes both as a fuel as well as the reducing agent. So, the iron oxide will be reduced to iron, and this carbon will take out that O2 in the form of CO2. So, that is why it is used. It's that the importance of steel in the modern societies, and the use of coke is again quite well known. So, this coke is generated from coal, a special grade of coal, and it is having it should have like low ash content, then moisture and sulfur and etc. And obviously, there is a process of preparing this kind of coal or coke. It cannot come from all type of coals. Okay. There is some specific grade of coal, as I told you. Along with that, sometime we blend it different grades of coal. It is not like that everywhere this kind of special coals, bituminous coal will be available, and from those type of bituminous coal we try to get this coke. And how do we prepare this coke? It is basically produced in a coke oven, and that is generally airless heating chamber, and where it will be heated up nearly around 1400 degree centigrade. It ranges between 1200,000 to 2000 degree centigrade, and when it is in absence of air, basically there is no oxygen present in that atmosphere. So, all these volatile components which are there in the carbonaceous material or the coal, it will come out. So, it will come out in the form of gas, and the whatever is remaining is basically that is the carbonaceous material or the carbon, that part will be remaining, and that is the solid remnant is the coke. So, this gas or the which has been collected on the top of this coke, that is what is called the coke oven gas. So, you can understand the source of coke oven gas, and typically this as I told you that coke oven gas is the volatile component. We will see what are the things that are present in the next slide sometime. But typically if we look at 1.3 to 1.7 tons of coal will produce a ton of coke, and from there we can get nearly about 300 to 360 meter cube of coke oven gas. Now, this coke oven gas what does it do? I mean how it what it is comprising of. So, this is I mean I get this composition from the Barron's book. Typically if you look at, we have hydrogen, nitrogen, carbon monoxide, some amount of oxygen also, carbon dioxide, methane, ethane, heavier hydrocarbon and others. So, the majority or the main component of it is hydrogen. Then you have the methane, and the other parts are like nitrogen and other components. In carbon monoxide is also there, and some amount of ethane, ethylene, etc. will be there. And volume composition is also given, and but as I told you that this coke oven gas composition cannot be unique. So, if some blend of coal or a particular grade of coal is used for generating this coke, we will find certain composition of the coke oven gas, whereas if some other sources of coal is used, then this composition will obviously change, and say another kind of composition I have received from this paper. Here it is telling that there is a hydrogen in the the volumetric composition of hydrogen in this coke oven gas is between 55 to 60%, and the second major component is obviously the methane. There is no difference between these two, like this the majority part or the main component is hydrogen and the other is methane, and rest of it could be hydrogen nitrogen and carbon monoxide etc., other than the heavier hydrocarbons. Sometimes this hydrogen sulfide will also be there in small quantity, and depending on again the composition of the coke oven gas. Now, let us look into, once we have this composition known to us, then we can look into the normal boiling point of all these components present. So, here this is the composition that I have shown you first. So, these are the normal boiling point of different components in Kelvin. So, hydrogen is already you are familiar with this, its normal boiling point is 20.3 and nitrogen is 77.4, carbon monoxide, then oxygen and methane is the among this is the highest. Okay, not only the highest, but there are other components. So, methane is the one which is having 111.7, and the heavier hydrocarbons will obviously will have higher boiling point. So, like if we have this propylene and ethane and ethylene, so they have normal boiling point like 226, 184.5 and 169.5 respectively. So, these are the typical boiling point of the different constituents or components of this coke oven gas. So, what is let us look into the other one. Here also there is the similar kind of ethylene is only added part here 169.5 and ethane is 184.5. So, these are the kind of normal boiling points of the liquid sorry, of the gases or the composition of this coke oven gas. And you can see that there is a large difference between say this whole range with this hydrogen. So, the normal boiling point of hydrogen is widely different from all these components, other components. So, we can take advantage of this to separate out this. So, obviously, for separating out into its different compositions or different components, we need to cool it cryogenically. So, one such process that we will be talking today is basically the Lindebrand process, which has been invented long back sometime in 1924, and that has been in use for a completely different reason, that is basically to produce the ammonia. So, in ammonia you know that its composition is NH3. So, it is in NH3 we have one part of nitrogen combining with 3 part of hydrogen. So, it should be the composition should be finally the product that should come out should have 1 part of nitrogen combining with the 3 part of hydrogen. So, that is the kind of composition this Lindebrand process is supposed to have, but finally, if we want this it is not of course making the ammonia, but it is making a composition or gaseous composition of 1 part of nitrogen and 3 parts of hydrogen. So, from there we can also separate it out this hydrogen from nitrogen. So, we will see to that. Initially what we will try is to separate this nitrogen and hydrogen from this gas, and then we will go to the different what is called I mean the process, let us see, and then we will try to separate out this nitrogen and hydrogen. So, first of all, this coke oven gas is pressurized to nearly 1.3 MPa or nearly about 13 bar in a compressor. So, once we compress it, then we first of all cool it with the help of liquid ammonia refrigerant. So, then it is like this, we will be connecting this this compressed gas will come over here, then it will pass through this 2 stream exchanger, and from here it is coming, and then we will take it to another, this is the 3 stream exchanger. We will try to identify all the streams later on. So, this is how it is coming from the compressor to the first exchanger, and this is this exchanger in the first exchanger, as I told you that it is cooled with the ammonia. So, we are using ammonia to cool this incoming high pressure coke oven gas. Then it will come to a 3 stream heat exchanger. From this 3 stream exchanger it will be cooling partially this coke oven gas, so that we can take out some a part of the propylene, for example. Okay. Say the propylene will be coming out from here, and then it will the other part this is basically it is coming to a, this is called a phase separator. This phase separator will separate out the liquid portion, and the gaseous portion will come as it is, fine. So, the coke oven gas is whatever propylene was there is getting condensed, and it is coming out, this rest of the components are coming out in the compressed condition. So, then it comes to another heat exchanger. Here this will be, say if it is getting cooled to nearly 45 degrees centigrade, this will be cooled to nearly about minus 100 degrees centigrade in this 3 stream exchanger, and then it will be coming to this third heat exchanger, where it will be cooled to minus 145 degrees centigrade, when you will find that some of the ethylene and is getting condensed, and a small portion of methane will also be condensed. So, here this is coming over here, then again you have the phase separator from where, as I told you, that ethylene will come out. Okay. So, once this ethylene is getting separated, the rest of the gas, I mean compressed gas will come, and from here it will come through this 4 stream exchanger, then it will come to a condenser evaporator. So, what is that condenser evaporator? Here up to this part, it will be cooled to nearly about minus 180 degree centigrade. So, at minus 180 degree centigrade, you will find that it is not, it is condensing some of the methane, but methane will not be condensed completely, that we have to condense it in a what is called condenser evaporator. So, from here this high pressure methane and the other components, say hydrogen, nitrogen, CO and the methane, all are coming over here. So, this is basically a tube assembly and connected on the top. We will see later on about the detailed structure of this condenser evaporator. So, you can see that this is coming to the tube side, and this tube side, it will be getting cooled. The tubes will be cooled with the help of some refrigerant. So, let us have a look into the refrigerant that we can provide. One such refrigerant would be the liquid nitrogen. So, if we have LN2 here, this liquid nitrogen will come, and that will be coming over here to this, and it will be coming through expander. This this is called JT expansion. After this JT expansion, this will be provided over here. So, on this side, on the cell side, I mean on the tube's outside part, it will be it will be cooled with liquid nitrogen. So, we are providing liquid nitrogen. So, obviously, some amount of gaseous nitrogen will also, this nitrogen will evaporate. So, this will come out like this. This is the vapor nitrogen that is coming out. So, what is happening here? These tubes will be cooled with liquid nitrogen to nearly about say minus 190 degree centigrade in this condenser evaporator. So, here at this point, what we have is as we told, that it is comprising of hydrogen, nitrogen and some amount of methane. Methane will be getting condensed and it will be stored over here, and there is also some amount of nitrogen in it. Okay. So, this part which is getting collected on top, it is basically the hydrogen plus some amount of nitrogen and CO, and the methane is getting condensed over here. So, from here we will take out this mixture. This will not be only the methane. Methane will be mixed. The primary component will be of course methane, then along with that 70%, 74% say methane would be there, and there would be some amount of CO, about 10% of CO would be present in it, and from there this will be taken back to through this heat exchanger. It will go back from here, and this will go back finally to, and it will cool the incoming high pressure gas. Okay. So, this is what is the methane when it is coming out. This is methane gas, but when it was coming out from this condenser evaporator, it was in the form of liquid methane. So, that is about methane, and what we are left with here on the top of this vapor, this dome. This is basically the nitrogen, hydrogen and CO. So, you see that our target was to get hydrogen and nitrogen mixture with a ratio of nitrogen 1 and hydrogen 3. So, that we have obtained with the with an additional component CO. So, this can be we can get rid of this CO with the help of CO scrubber. So, this is what is the CO scrubber, and it is basically this component, this mixture will be coming at this bottom, and it will be as if we want to wash it with the liquid liquid nitrogen. So, here you may remember that earlier we have provided some refrigeration with the help of this liquid nitrogen. So, this liquid nitrogen, a part of that liquid nitrogen is now coming into this CO scrubber, where this will scrub this CO part, okay. It will be dissolved in that along with this hydrogen and nitrogen. Those will be collected on the top. This will be hydrogen plus nitrogen, and this is the product that we are looking for. So, finally, so we will be taking this product from here, this N2 plus H2 from this point, and that will come over here, and then it will come as a product from this part, and while coming out it will be cooling the incoming high pressure coke oven gas, which we have shown earlier. Now, at the bottom of it, as we have understood that this again this some portion of this CO, mainly it would be CO, and you are washing it with the nitrogen. So, this CO N2 and a small portion of this CH4 will also be present here. So, this is CH4 is about 7%, N2 would be about majority 73%, and CO would be about 18%. So, these are the kind of composition we will have at the bottom of this CO scrubber, and this is at low temperature. Definitely before we throw it out, we want to take out its cold part from here, and then we will put it in this heat exchanger. So, that will provide its refrigeration, and this will come out from here, and this will come out finally as N2 and CO mixture in the gaseous form. It was in the form of liquid at this point, and its cold part has been retrieved all the way, and there is another stream. We have produced some kind of ethylene, we have said, and this ethylene will be finally pushed through this 4 stream heat exchanger. So, we have couple of heat exchangers. Along with that, we have this condenser evaporator. Along with that, we have a CO scrubber, and most importantly, we have this coolant liquid nitrogen. So, that we have to supply it in this process of in the lead bond process, that is again has to be supplied along with other this coke oven gas. So, now what we have obtained is basically this a mixture of hydrogen and nitrogen. Basically, this process was meant for, as I told you, that for ammonia mixture, ammonia gaseous mixture. So, that means that we have this H2 plus N2, and now if we want to have this H2 out of this mixture, again I mean that is the question, how do we do that. So, let us look how we can finally do that. What could be the possibilities? So, if we have again liquid nitrogen with us, we will have this mixture with us, that is nitrogen and 3 parts of hydrogen. So, what we will try to do is that we will use another condenser evaporator. So, what we will do is that we will take this mixture and we will put it on this side. So, here we will have the again liquid nitrogen, and this would be the gaseous nitrogen. That gaseous nitrogen will come out it will evaporate, and from here you are supposed to get the hydrogen which will be collected on this dome part, and here this is this is again Ln2. This nitrogen is getting condensed over here, and with the help of this liquid nitrogen that you have supplied here on this tube side, and this is what is the gaseous nitrogen that is coming out of this system. So, that is about this condenser evaporator part to produce the pure hydrogen from the coke oven gas. So, this complete process which I have drawn with the lines, you can have a look into it. The thing is that here we had the precoolant ammonia, and it was this coke oven gas which was coming here. It was cooled initially with the ammonia, then there is a 3 stream exchanger, 2 3 stream exchangers are there. Here some amount of propylene was extracted, then we have the ethylene that has come out from here. Then we have this 4 stream exchanger, it will come over here, and this will come into this evaporator and condenser. Finally, this is the mixture of N2 H2 and H2N2 plus CO, and this CO we get rid of using the CO scrubber. Here we have Ln2 supply, this Ln2 is also fed into this CO scrubber, where this CO part will be scrubbed out or washed out from this in this CO scrubber part, and from the top of it that has been taken out. Okay, fine. So, from the this part we have taken out this N2 and H2. From here this is what is that H2 plus N2, which will be taken as the product, and that will come out from here. So, that is about this Linde-Braun process. So, you can cross check it if I have drawn anything wrong in the earlier process. This is the complete circuitry for the process diagram for the Linde-Braun process. So, let us have a look into this again. These are the references we have, and to conclude with we have that we have identified that this coke oven gas is a potential source of hydrogen, and that can be Linde-Braun process where liquid nitrogen is used as the coolant can be used to separate out this all these components of coke oven gas, and from there we can separate out this hydrogen. So, thank you very much for your attention.